the last set of reactions that we have are the SN1 and the E1 reactions. Now, let's consider this reaction right here. Tert butyl bromide with ethanol. That ethanol not only is our nucleophile, our base, but it's also our solvent. So for SN2 and E2 reactions that are concerted, we would want a polar aprotic solvent. Now that we have a polar protic solvent, these actually stabilize the cation that could form a positive charge because of the ability of the oxygen to have ion dipole forces. And so what we see in this reaction is not only a mix of substitution and elimination products, but what we will also see is that the only way to get that tertiary center to undergo a substitution is if it is not via an SN2 concerted reaction, right? Ethanol is not strong enough as a base. So SN2 is not possible. E2 is also very unlikely because of the strength of ethanol. So what it turns out is that this reaction instead follows first order kinetics. The rate of both of these reactions, the substitution and the elimination, will only be dependent on the electrophile. We don't care about the base or the nucleophile. They're not part of the rate determining step. So it's important to be able to walk through these mechanisms to see the similarities and the differences. The mechanism of substitution and elimination in this case start with the same step, the ionization of the substrate or the starting material, which in this case is the loss of the leaving group. Bromine is going to leave so that we can form ions. Bromine, remember, is a halogen. It has 3 lone pairs. By leaving, it becomes that stable conjugate base that we talked about. It's a good leaving group, but why this reaction can be seen as a first order reaction, loss of leaving group by itself, is because we have a carbocation as well. So remind us of our carbocation stabilities. Allylic is the most stable carbocation, then tertiary, then secondary. Primary and methyl carbocations rarely form. What we are going to see is that SN1 and E1 are really good for tertiaries and allylics, but also secondaries can undergo them kind of, sort of, not very well. They're really slow, but rearrangements can occur to help stabilize those secondary carbocations. Now from here, after that first step, that rate determining step of loss of leaving group, this first step can actually funnel us in to both the substitution and the elimination. Again, for abbreviation purposes, SN1, nucleophilic substitution unimolecular. Only one molecule is dependent for that rate determining step. E1, elimination unimolecular. After that carbocation is formed, it will either undergo a substitution or an elimination depending on how it reacts with the solvent. The substitution reaction, so we're going to write it over again. The substitution reaction will look like this. Two-step process starts with the loss of leaving group. So bromine picks up its electrons and runs. We get a carbocation. I'm going to write Br minus down at the bottom so that it's not clouding my view of the next steps. We want to think about the nucleophilic attack coming in next. Ethanol is going to come in for our second step of nuke attack. Remember, the more reactive nucleophile will attack that carbocation. Br minus is not the more reactive nucleophile. Think about the stability of both of these as bases. Br minus comes from HBr, which has a pKa of -9. If you think about a protonated alcohol, that's about -1.7. So ethanol is a more reactive base than Br minus. It's kind of a weird thing to think about since we usually attribute that minus charge with reactivity. In this case, look to the pKa's and look to understanding those differences. Even ARIO, Br minus is much more suited to hold a negative charge than oxygen. And in this case, oxygen here, even though it's not negatively charged, is a much stronger base. What we end up with is we have to do a little bit of a cleanup step at the end. So thinking about that nuke attack, the last thing that we want to be able to do is clean up that oxygen with the formal charge of +1. We'll use another equivalent of solvent to do a final proton transfer, step number 3. Why we need to do this is so that our final product, our ether, is not protonated. This is our final substitution product. The entire mechanism is 3 steps. That last step is just a proton transfer to make sure that we clean up our final product. This is also called solvolysis because the solvent is acting as the nucleophile here. The highest energy intermediate, notice that we have 2 intermediates here, intermediate 1 and intermediate 2 with our reactant and our product. We'll construct the reaction coordinate diagram in class together, but it is a 3-step reaction total, the last step just being a proton transfer. The overall loss of leaving group and nuke attack is what the textbook does focus on as the main 2 steps of this reaction. The first intermediate is higher in energy than the second intermediate. Carbocations are very unstable. They're carbons with a lack of an octet. That's the reason why they have the +1 charge. Notice the oxygen there has a formal charge of +1, but it doesn't have a lack of an octet. It's just having an extra bond. All right. The E1 mechanism, the reaction of this tertiary substrate, starting material, again, starts with the loss of leaving group. Step number 1. That is the step that is most important to look at. Will this reaction happen? It's the rate determining step. Did I make a carbocation that is stabilized? That makes sense. And then what we want to establish for our E1 reaction is we have alpha and we have a variety of betas. All 3 of those carbons that are beta are identical. They're all identical. They're all methyls. So I'm just going to pull off 1. Excellent. And then ethanol will come and do the second step of our proton transfer. We roll that pi bond down in between alpha and beta. There's alpha, there's beta. We also do make a protonated ethanol, and we also have Br minus floating around in solution. So just some general ideas here. The rate of the E1 is the rate law is the same for E1 and SN1. In both cases, that first step is the rate determining step, the slow step, right? And so when we think about ethanol here, it's serving as a base as well as the solvent, right? So same kinetics when we think about what affects the rate of the reaction. It's the electrophile, right? It's not going to be the base or the nucleophile that is unimportant. It's in a subsequent step, and it's not going to be the slow step. So really what we want to be able to think about with the SN1 is we really just see tertiaries and allylic carbocations. Sometimes secondary carbocations can undergo this reaction. For the E1, the same thing, we still need to make a stable carbocation. And so we can just think about copy, paste. Lovely, right? Really important to get that idea of what is required of that electrophile, since it is the rate determiner. So again, here's the reaction coordinate diagram, at least for the first two steps of each E1 and E2. It's nice to compare these two. Both share that first step, reactants through transition state 1 to our first set of intermediates here. Then they diverge after that to a second transition state. And so it's important to be able to identify what type of a reaction are you doing. Now, rearrangements can occur, right? So when we look at this reaction, I would look first and say, okay, there is a secondary alkyl halide. Cool. Let's look in water. This is a weak nuke, and it can also be thought about as a weak base. So right now I'm focused on the E1 and the SN1. Both of these reactions will happen. But notice after step number 1 of my proton transfer or my loss of leaving group, I have a secondary carbocation, and adjacent to it, right next door on what would be my beta, there's a more substituted center. So all those carbocation rearrangements that we had before, 1,2 methyl shifts, 1,2 hydride shifts, they can occur here. They will. Remember, intramolecular reactions are way faster than intermolecular. So that water is not going to come and react until that carbocation has already shifted secondary to a tertiary. Definitely more stable. Then we can keep going. Let's look at water just as our SN1 reagent first. Woo, there you go. Do our nucleophilic attack. We will need to do a proton transfer on this as well for our last little cleanup step. Water can pull off that proton to make our final substitution product, the alcohol. But notice how what we originally called our alpha carbon is now changed, right? The actual carbon that got the substituted product is now different. All right, same thing. I can take this guy, and I'm just going to give myself some room and use water for the E1 reaction. And if this is alpha, I have some options for beta. Beta 1, same as over here, beta 1. There's an H there though too. Don't forget beta 2. I'm just going to erase one of the beta 1s because they're the exact same. I'll deal with beta 2 first. What's good to note, again, while we're getting used to this mechanism, is there any stereochemistry, cis or trans? There is still a stereoselectivity with this reaction. We like trans versus cis, but there's no anti-periplanar with the E1. There's no backside attack with the SN1. So we make all sorts of racemic mixtures and all sorts of chiral centers. I'm going to just present here alpha, and I'll hang off beta 1. Draw another water. I'll put it right up there though for my E1 with my other beta. That plus charge. Again, neither of these have stereochemistry because each one has at least one side where there are identical groups. So there's no prioritizing with these two. But in terms of stereoselectivity and regioselectivity, if we did have cis and trans, we would definitely favor the trans over the cis. Here, with all three of these products, 1, 2, and 3, we will definitely favor our elimination product that is more substituted. Water is very, very small, so we can think about those E1 reactions always giving the most stable alkene possible. All right, so we can think about solvent, and our last idea here is understanding our polar protic solvents. So notice this is a tertiary alkyl halide. It's going to form a carbocation in that first step, loss of leaving group, the rate determining step of our SN1 and E1 reactions. Notice the difference between polar protic solvents and that relative rate of reaction. So how much, you can think about this as product amounts, right? They're normalized so that you can see the difference. Water is very good at stabilizing carbocations because of the two areas of hydrogens of delta pluses and oxygen being very available with its delta minus to stabilize positive charged things. And as you get down to the polar aprotics, notice these values right here, they're very, very low. Polar aprotic solvents with our SN1 and E1 slow the reaction rate down drastically. So make sure that we are identifying when we form a carbocation, we want polar protic solvents, things with a polar proton. And when we have our non-carbocation reactions, our concerted reactions, SN1 or SN2 and E2, we want our aprotic solvents, the ones that don't really care about stabilizing carbocations. Again, the regioselectivity here, just to sum up and to finalize, just like with E2 reactions, it is possible for E1 eliminations to result in more than one regioisomer, regioselectivity, Hoffman versus Zaitsev. E1 will always give the more substituted alkene, just always. We cannot control the regioselectivity like we did with big or small bases. E1, because of the carbocation, there's a limited amount of steric hindrance at any rate, so we will always get the more substituted product. No Zaitsev or Hoffman control. It is further possible to obtain several different alkenes, right? So many things open up with our E1 reactions. And so again, we'll get all different products, but the E isomer is always more favored than the Z isomer. So analyzing that substrate, what's really important to note is when things are more favored than others, what we will pretty much see is that primaries will have major for the SN2 when you have that strong base and the strong nucleophile, those oxygens with the minus charges. If you have a secondary, it will favor E2 over the SN2. Everything else is pretty much structured when we start thinking about having a strong base or a strong nucleophile. So take the time to really analyze everything on the substrate to help you know which mechanism will dominate. Notice over here on our SN1 and E1s, that idea that we will definitely see them equal, 50-50. I won't ask you who's major or who's minor in SN1 and E1. Okay, let's dive into some other substrates that can do our SN2, SN1, E1 and E2 reactions. These are other good leaving groups. One class that we're going to look at is called the alkyl sulfonates. We talked about this at the very beginning of our chapter 7 discussion when we were talking about other good leaving groups other than the halogens. Why the sulfonates are good at leaving is because of the resonance that they have when that group leaves. So imagine that we can just think about that leaving group. The oxygen here with the minus charge is quite different than an oxygen, say, for an alcohol, because it's bonded to a sulfur that has other pi bonds. There are tons of resonance structures. We can think about the one going up to the top. We can think about this one down at the bottom. There are tons of resonance structures that the sulfonates can do that help stabilize. Looking at the different types of sulfonates we have mesylate, where that CH3 group is on there. The tosylate, which we will talk about, is more common with this benzene ring with the methyl on it. Common name for that is toluene, so tosylates come from that word. And then the triflate, which is the CF3 group, trifluoro group. They can be abbreviated. You can see their abbreviations NS, TS, and TF on that oxygen group. So these are excellent leaving groups. They're also really large, so we don't tend to draw them all out. We tend to just use their abbreviations. So with these, we can actually think about them being the same as an alkyl halide. You could see them being on a primary alpha carbon, and when paired with a strong reactive nucleophile, we can do the SN2 reaction, which we see here as the major. We can also do the E2, which would be the minor for that primary. For secondaries, remember when we have a secondary, the major product is the elimination reaction when paired with a really reactive nucleophile and base. So we have our E2 mechanism as our major product. Minor is the SN2 for that one. Again, remember the competition between our primary and our secondary alpha carbons. So now we can see that those tosylate groups or any of the sulfonates are really good leaving groups and can be treated the exact same as our alkyl halide leaving group was. So let's just think about how do we actually make the alkyl sulfonates. So we start with tosyl chloride, TSCl, molecule right here over on the side. But again, we like to abbreviate. So in this mechanism, what's really important to note is that we can actually abbreviate TSCl when we do these curved arrows. When we attack that TS group and kick off the chlorine, we are attacking the sulfur group and kicking off the chlorine leaving group on that group, on that sulfur, so that we can create a more stable leaving group. Alcohols, OH, is a very, very poor leaving group. So we get the TS group on there. Now, with the proton on the oxygen, that is not a good leaving group. Imagine that popping up and what you're actually getting is an OH on that sulfur. That looks like H2SO4, so it will not happen that way. So be sure to include PY, usually written on the bottom of the arrow. It's pyridine. That is simply a base. That base is there to deprotonate our oxygen, to make sure that our oxygen can be a better leaving group, to be the tosylate group. OTS. We get a protonated pyridine as a conjugate acid. You do not need to draw that. I just wanted to draw the both the product and the conjugate acid of that final acid base step. So we have a nuke attack with a loss of leaving group followed by step number 3 overall here, or curved arrow pattern number 3, proton transfer. That proton transfer is important to actually get the OTS group on there. And just to draw it out, O with the sulfur and pi bonds. TS is the tosylate group, so it has a benzene ring with a methyl on the exact opposite side. Alcohols are really bad at leaving groups. They can be used for substitution and elimination, but not in the same way that we saw alkyl halides. We can make that alcohol into a tosylate group, like we just saw, and that therefore can then undergo any of our substitution or eliminations we saw before in chapter 7, or we can do a different type of substitution and elimination reaction. One, not with a nucleophile or a base, but what do we see over the reaction arrow? An acid. Big difference here. When alcohols are the leaving group, OH-1 is reactive, so therefore it is not a good leaving group. So what we have to do is make oxygen a good leaving group. One way is to make it a tosylate. The second way is to protonate it with an acid. So we need a strongly acidic conditions to do this reaction so that H2O is the leaving group, not OH-1. So what you see in that first step is a proton transfer, followed by your SN2 nuke attack and loss of leaving group. Now, what's important to note is that a primary alcohol, what we have here, alpha carbon that is a primary, will undergo this reaction with SN2 conditions. If you have a secondary or a tertiary, you will undergo SN1 conditions, carbocation intermediate, loss of leaving group happens first, and then you will have your nuke attack. So again, SN2 conditions, we can make our primary alcohol into a primary alkyl halide via our SN2 reaction. We can do this reaction as well with our secondary and our tertiaries, just making note that this is going to undergo a proton transfer and then a loss of a leaving group. We will not have the backside attack occur here before the leaving group has left. So loss of leaving group and then nuke attack, right? SN1 conditions. Alcohols can also undergo elimination. We will use, again, strongly acidic conditions. This will get our alcohol to be a better leaving group. H2O is a much better leaving group. So here, starting with an example that is a tertiary alcohol, we see that tertiaries, just like our secondaries, undergo E1 reactions. We'll have that first step of a proton transfer, followed by step number 2, that loss of leaving group, and then the proton transfer to complete the E1 mechanism. These are great reactions to undergo similar elimination and substitutions with alcohol leaving groups. But again, remember, you have to do something different than our alkyl halides for alcohols. Alcohols are not good leaving groups. So either change that alcohol to a tosylate or use acidic conditions. Let's just again see for our primary, when we think about that water, I'm going to hang off one of the protons on H2SO4 so that I can see that we first do that proton transfer to make oxygen a better leaving group. And then we'll do our E2 proton transfer with our loss of a leaving group to complete our E2 mechanism. This only occurs with primary alcohols. Again, with our tertiaries or our secondaries, we first do our proton transfer, make oxygen a good leaving group, and then we will do our loss of a leaving group, make the carbocation, and then we will finish up with our final step of proton transfer, E1 for our tertiary and our secondary alcohols. So just to recap, for alcohols, you have one of two options. Make them tosylates. And then you can use any of our chapter 7, SN2, E2, SN1, E1 reactions. So this will work for primary, secondary, or tertiary tosylates as according to our primary, secondary, or tertiary alkyl halides. The other option is to use acidic conditions. If we do that, things like HBr, a primary alcohol, will undergo SN2, a secondary or a tertiary alcohol will undergo SN1. No way around that. Carbocation rearrangements will occur if possible. With H2SO4, a primary alcohol will undergo an E2 reaction. With H2SO4 and a secondary or a tertiary alcohol, we will undergo an E1. Again, carbocation rearrangements, all products available.